So hi guys, this is our project Robot Navigation with LLMs. Well, it is an attempt by us to make the robot more versatile. Me, myself, Adamya AI, my friend Priyanshu Maurya has been working on this during the last sem. And why do we need like LLM based robots? Well, to solve the problem of dynamic environments. Now, what is problem of dynamic environment? Well, to understand it, first of all, what is static map? Well, current robot use static maps to navigate from one place to other. Well, static map is like once you take the map of the area, then you never update it. And current robots are based on this thing. Well, second is real world dynamism. Well, if I move this keyboard from this place to somewhere else, then it won't be mapped, and my robot will get confused like where the keyboard is. And third is need for adaptability. Well, we want our robots to do more than just like if the keyboard is here, then fetch it. I want my robot to find the keyboard and then pick it up for me. Well, why we are doing this thing in applied instrumentation? Well, as far as we can remember, in PHN 310, we have been studying sensors, and robots use a lot of sensors to navigate and to do the task that we require them to do. Now, second is adaptive navigation. In applied instrumentation, we have been thinking in such a way that how do we apply our knowledge to solve a problem? Well, the problem here is navigation, and we are applying our knowledge of AI to make it faster and better. Now, third is control system. Well, in applied instrumentation, we have learned that we get data from sensor, and we have to do something to it to make it valuable to us. Now, here the same thing is like control system. We get data from our sensor, and then we use them to move robot from one place to another and run advanced algorithms to like for decision making and to navigate.
Now I would like to continue building a map. What we need data in the data acquisition is image data, movement data, and comprehensive mapping. For the image data, we can use depth map and the camera sensor itself to get the image data. And for the movement data, we are going to use IMU sensor data, that is accelerometer data, GPS data, and the magnetic data, and the gyro data. And for comprehensive mapping, we are going to use depth sensor and the lidar sensor itself to get the comprehensive mapping of the object in the room or in the house. Next slide. And as we presented in our proposal PPT, we are going to use old phone as a sensor. And here is the list of available sensor in the old phones, like you can see accelerometer, gyro sensor, and here is the data getting from the accelerometer, gyro sensor, and magnetic field plot on the movement of the phone. Next PPT. Now we look to the working of sensor. First of all, we have here the accelerometer, and in which we can see there are two types of electrode. One is fixed and one is moving. And when there is some acceleration, the moving electrode move, and there is some change in capacitance that we calibrate to get the acceleration. And if we talk about the gyroscope, it works on the same principle, but little bit more complicated structure. There is a regular oscillation between these electrode, yellow electrode, and when there is some rotation, there is some change in the capacitance that is calibrated to get the rotation. And if we talk about the magnetic sensor, it works on a Hall effect, in which there is a Hall voltage generated due to the magnetic field of Earth, and when there is some change in position, the voltage changes across the plate, and that's how we know the position and the magnetic field. And it is used to get the direction also. And here is the IMU sensor that has these all three: magnetic sensor, accelerometer, and gyro sensor. Now, if we talk about the depth map calculation, we have two methods. First one is time of flight method, and second is stereo vision. In the time of flight, the light goes and strike the object and come back to the sensor, and we notice the time of flight and get the distance of the object from the sensor. And in stereo vision, we use two camera sensor and calibrate it in a such way that using the disparity, we can calculate the distance of the object from the sensor. Next slide. Here is the calculation part for the stereo method which we are going to use. We can see there is the point, observation point and image point P1 and P2, that is made on the sensor from camera 1 and camera 2. The location of the point in camera 1 is x1 y1, and location of point in camera 2 is x2 y2. And if we have to calculate the disparity, disparity is simply the difference between x1 and x2. And to calculate the depth, and we know the focal length of the camera, then the depth will be focal length into the baseline distance, that is between the camera 1 and camera 2, divided by the disparity. Next. Now coming to the part that we explained that we said in the proposal that we are not going to use the depth sensor. In, in place of that, we are going to use the DL model that will do the part of by taking the studio images by ourselves. So first of all, we need data collection data. Then we train our ML model, and then we test the depth mapping. Next. Here is the state of the art architecture for calculating the depth map that we used. You can see that the architecture of this, and it has some RNN component that create a heat map according to the distance of the object. Next. For the training part, we have stereo images, left image, and right images that we fed into our model, and it tasks to predict the heat map that shows the heat map, or we can say disparity that shows the distance of the object, and the data set is the KT data set. Okay, good. Next slide. Here is the result of the model. Like you can see in the above part, there is a heat map. The closer the object, the reddish the image, and the for the object, the bluish the image. And you can see there is some boxes around the cars that is for we use YOLO V4 for the object detection. It's pretend, and the distance is calculated by the formula that we shown earlier. Next. Here is our video on the testing data. You can see. Okay, next slide. Now for mapping and localization, I would like to call Priyanshu. Pansari.
Now to retrieve the data, we would like to interpret the data to control our robot. For that, we have first mapping and localization. For that, we use something called R-type map. That is a SLAM algorithm. SLAM algorithm is a simultaneous localization and mapping algorithm. What it does, it takes the data from LiDAR, depth sensor, and IMU to create a map by detecting features, and it detects the features and identify when it's occurring again to create a loop closure by which it perfects the map. I will show you a demonstration in the following video. Here you can see the map is being formed by the robot. The robot is exploring, and as you can see, when it's complete the loop, it detects the features that's being repeated and creates a loop closure to create a better map. Now we are showing a video of using camera for R-type mapping. Previously we were only using laser. This is when we include the camera. You can see. So now we have navigation. So what we have map. So how we navigate using it? We have a global planner and local planner for it. Global planner finds the path to the final goal by dividing the complete part into some small parts. Then local parts control the robot to move from the current location to the nearest point. For that, what it does, it uses algorithms to detect the obstacles and to steer clear of it. We have two planners here, which is basic row stack. So here is an example of local planner. You can see the local planner trying to you can see local planner going to the location that is the green point and avoiding the pink point, which is obstacle. It creates multiple paths, that is the yellow lines, and choose one of them which is not in line of obstacle and in the path of the goal. For global planner, what we do is we take the starting point. From this we propagate the paths. Then from that path we again propagate the path to get this T kind of structure. And from this we get various paths that lead to near the goal. From that path we assign a cost to each path, which says something about the quality of the path, and we take the path with least cost. Then we have recovery behavior. So when the robot gets stuck, it starts a clearing rotation. If this doesn't clear the robot, it doesn't aggressive reset, where it gives the motors high torque. If it is not again clear, then we abort the motion. So for the manipulator, we have an arm in our project. To control that, we are using Movit motion framework. What Movit does it uses inverse kinematics to calculate the joint angle such that the endpoint is at our required position.
Now, how are we using LLMs here? Well, we are using LLM for supervision of robot. We are using LLM for contextual understanding. So, if you say a robot to find your dog, then your robot doesn't understand what you are saying. For that, we are using LLMs. We are using LLMs for task planning. Now, if a robot want to go to some other room and fetch a bottle, then our LLM will tell it in which step to do this task. And then we are using error handling. If you didn't find the bottle in that room, then that's an error. And to handle that, we are also using LLM. Now, our basic architecture is first we map the data. Now we identify points on it to convert it to graph. Then we go to each node on that graph and take images. Then we pass it through our vision model. Then we generate some text data through it. As images are not that much useful for LLMs, so we are converting it to text data. Then we store that data and load it to the prompt. Now suppose we get a query from the user. So this query goes to the agents. Then this query get loaded into the prompt that are predefined for an agent, and then it complete the task. And while completing the task, it will visit some nodes. And while visiting that node, we'll take the pictures again and update the data so that we are not using static maps for our robot. Now here's our so we are using multimodel multimodels to convert images to text. And as you can see, this is our prompt to convert image data to text data, and this is the result of this model. And now approach that we are used for LM is like using two agents, and we have tried using different things like RAG and putting the whole data into the prompt itself. And after testing it, we found out like this is the best approach that we can use, which is use two agents. First is finder, second one is decision maker. Now, what finder does is it find the room of interest, and decision maker decides like after reaching that room of interest, what needs to be done. Now, here's like overview of agent working. So we receive a query by user. Then first it goes to LLM finder. It gives us a point of interest. Then it goes to the navigation point. Like it navigate to the point of interest. Now here the decision maker makes a decision. Like if I have completed the task I was asked to do, or if not fine, then what I should do. Now if not, then it goes back to LLM finder. Repeat the same process. And if found, then LLM task provider, it goes to LLM task provider and move the hand accordingly. And also while visiting each point of interest, we are also updating our data as explained previously. Now this is an example, like if we want to go from point room 2 to room 7. So this is, we just have to solve this graph, which is a basic algorithm. Now we did a demo test in our hostel. So first thing we did was asked our LLM a basic thing. So we want to find it to find the laptop, and these were the room details that our model had. And the answer we got was room of interest is room 1, as it can see that the desk contains the laptop. Now we thought like, why not give some complex query? We asked it go find some papers. Now the first response that we got was very interesting. We got like go to room 3, and this room 3 has an elevator lobby, and elevator lobbies usually have papers on their walls. Now we went there, but there was no paper found. Then we go back to our finder and we asked it again. Now, what the response we got is like, go to room 1. Explanation is here, like, room 1 contains a desk with a laptop, books, water bottles, and other objects on it. And books contains paper. Like, it can also complete complex tasks. Now, the objects that we have used in our simulation are depth model, our move based LiDAR, and this is the structure of like our model, like our demo model that we are using in simulations. Now, Pansari.
You can see here is the simulation of arm. We can provide the arm the end endpoint, and it can complete the path that is required for the arm to reach that point. Then we have the simulation. In the simulation, we can give the robot some end goal, and the robot will move towards that goal using the global and local planar. And while it's doing that, it will create a map. It will fine tune the map that is being created. You can see here the 3D structures that's been created are the map, and the black are due to LiDAR. So where's the prototype? The thing is that when we were creating this, we had a 2 semester deadline. In the first semester deadline, we wanted to complete the rover part. In the second semester, we wanted to complete the arm part. But due to some technical difficulties we were facing in simulation, we decided to prepone the arm part. As you can see, we have at least done the arm part in simulation. And for the prototype, we have this rover which is working. We can give it velocity and some rotation, but we haven't applied the complete algorithm in it.
Now, for those of you wondering, like, this is easy, you should be doing it within 1 or 2 months. Well, I guess then you are not familiar with ROS, as in ROS, while you try to do something, then a lot of error pop out of nowhere, and we are trying to integrate conventional ROS with LLMs. So this was the reason, like, we were facing error at every point, and while trying to solve them, we were facing a lot of problems.